Yeah, welcome to the Turing Spotlight session. Sorry, I've actually missed the last one of these, so I'm glad to be back. And we've got two great speakers today, Manuel López-Ibáñez and Neil Walton. And I think Manuel is going to kick us off, and he's going to talk about automatic component-wise design of algorithms for optimization, machine learning, and robotics. So over to you, Manuel.
Thank you, Magnus. Can you see my screen? Is that okay?
Yeah, that's fine, yeah.
Okay, so let me start the timer. So yeah, like Magnus said, my name is Manuel López-Ibáñez. I'm a senior lecturer at the University of Manchester and also a senior distinguished researcher at the University of Malaga in Spain. And I'm going to talk about basically how can we automatically design algorithms as a general approach for automatically designing algorithms. And here you can see a picture that kind of summarizes what I'm going to talk about. It's a picture provided by my colleague and friend, Johan Dreo. Unfortunately, I won't have time to describe all the details in this picture, so this is the last time you're going to see it. So let's start. The first thing I'm going to focus is on optimization. And if you have never heard of optimization, the idea behind optimization is that we want to find solutions that maximize or minimize certain objectives and satisfy certain constraints. And optimization problems are everywhere in manufacturing, in logistics, in communication networks, in bioinformatics. Everywhere you look at, there are optimization problems to be solved and being solved every day. And we have many types of algorithms for solving optimization problems. And one of these types is multi-objective evolutionary algorithms. These are algorithms that there is research about them for more than 3 decades. And it's probably one of the most researched types of algorithms for problems with multiple objectives, where you want to simultaneously optimize several objectives. And they have many applications in real-world domains, a large number of high-quality libraries and frameworks available where the algorithms are already implemented. For example, this Platimo library implements, I think it's more than 100 of such algorithms. And that is one of the issues. There are many algorithms of this type, and it's not always easy to know how to select the one that you want to use in practice. So of course, what we did is to propose our own multi-objective evolutionary algorithm, MOEA, and we call it AutoMOEA. But there is something special about AutoMOEA. This AutoMOEA was not designed by us directly, but was designed by a different algorithm. In this case, an algorithm called IRACE. It was designed by taking the components from human design MOEAs and recombining them in a different way. And what we did is benchmark this AutoMOEA that is based on the same components as the other algorithms, using the same benchmark that those algorithms use. And the result was quite surprising because it was able to clearly outrank the human design MOEAs in all those benchmarks. In fact, if the benchmarks differ from the standard ones used in the field, then the difference, the advantage of AutoMOEA grows further. And this is joint work with Leonardo Becerra and Thomas Stusle that is explained in these 2 publications. So what is actually AutoMOEA? Because it's not an algorithm itself, it's more a framework for generating new MOEAs. And it's a framework that is built by taking parts from other MOEAs and allowing these parts to be recombined in ways that were never tried before. How does recombination happen? This recombination happens by setting specific parameters of the framework. The framework has 17 high-level parameters that control the design, that control how these components are recombined, and they are all categorical. And 20 low-level parameters that are mostly numerical that control various things. This allows us to generate, in principle, hundreds of thousands of valid MOEAs, many of them probably very poor, but some of them seem to be able to optimize performance for particular benchmarks. And then we have a way to automatically search the space of designs to find optimized designs. When we compare this to the traditional design of MOIAs or in general optimization algorithms, we have quite a different approach. In the traditional design, what we have is an expert that has some benchmark problems or data sets, and they invent using their intuition, or they take some design choices and probably several design choices that end up making up a solver or an algorithm. And during this process, some design choices are discarded, or simply the expert was not aware of them. And using trial and error and statistics, the expert decides on a solver, and this is the algorithm that will be used in practice. Hopefully, the problem instances that arise in practice are similar to the ones that the expert has used when designing the algorithm. And then the solver somehow becomes some kind of monolithic block with a label attached to the side that is published in a paper and cannot change. But we know this is not true. We know that inside these solvers, typically there are components that are the result of design choices made when creating the algorithm. And these components could be replaced by alternative components. And this is the motivation for this idea of component-wise automatic algorithm design. So the idea is that let's open the space, let's define this design space, and let's have available these components as a library of components. And then let's define rules that actually lead to creating valid designs by combining these components. And whatever way we define this design space, this can be by means of an algorithmic template, or it can be by means of a grammar description. We can always convert this design space into a parameter space made of numerical, categorical decision variables, possibly with constraints that we can optimize. When we set settings to the parameters of this parameter space, we are generating designs, but we don't want to search ourselves the parameter space. Normally, it's very large. So we use specialized algorithms that are called automatic parameter configuration tools or hyperparameter optimization tools to automatically search this parameter space, given some performance criteria and some examples of problem instances that are of interest or some interesting data sets, in such a way that when we find an optimized design, we are actually designing an effective algorithm for the particular application scenario that we are interested. Maybe you are already doing this. Maybe this sounds already familiar to you because it's not a completely new idea. This is something that is already going on in optimization. There are many of such frameworks for automatically designing algorithms. But it's even more prevalent in machine learning, where this approach can be thought as a subset of what is AutoML, or as an important part of AutoML. There are several of these frameworks like AutoWeka, AutoSKlearn, and maybe you have heard about Recipe. It's also something that is starting to be used in robotics. Normally in robotics, you use neuroevolution or other approaches to directly design the control software of a robot. But some projects, for example, this Automoded Chocolate or this Demiurge project, what they do is, well, let me show you the video that they have, and I will explain you what they do. So, sorry. No. So basically what they have is they want to automatically design the behavior of a swarm of little robots. And these little robots can have different hardware components, they have a library of already implemented behaviors, like, for example, communicating via lights, following each other, following a light, following a trail in the ground, leaving a trail. These are components that are very, very simple, but they are very precisely implemented. And then what they want to do is to define rules that combine these small components in such a way that the whole system doing different different combination of components, the whole system actually generates a collective behavior. And they use the same approach, the same structure that we use, for example, for Automoea. In fact, the algorithm that is searching for this collective behavior from the space, the design space of components, is the same that we use for Automoea. It's an algorithm called iRace. Okay, so normally when I give a presentation like this, I give several reasons why this is such a good idea. But I'm going to focus on the last reason, on reason 5, which is for me the most interesting, which is that this is a more interesting way, a more fun way, a more useful way to do research, at least what I believe researching in optimization. If we compare the classical way we do research in optimization, is that we have a human that designs an algorithm, normally with the goal to outperform other existing algorithms. And once they manage, they do some analysis of this algorithm that has been recently designed in order to publish a paper and be done with it. And then this algorithm will have a name and will be known with this name. If we have a system that can generate new algorithm designs from components automatically, as I described before, then the perspective changes. There is a paradigm shift there. So if we have this system that can automatically generate new algorithm designs from a library of components, then the role of a human is to devise novel algorithm components that are not already in the system. And then we can leave the task of finding the best combination of the components or searching the design space to the machine, to a CPU-intensive tool that can use data or examples of problem instances to try to optimize some performance criteria that we give to it by finding a design that from this design space. And then when the process is finished, we can use the data that the whole automatic design process has generated. That is not the data only about the final design returned by the system, but contains also information about things that didn't work and combinations of parameters that were unsuccessful. And use this analysis of the generated data to drive the improvement of the existing components or develop new components, and then start the cycle again by extending the system with these new components and see what happens in the next step. Of course, nothing is easy, and there are several challenges in applying this approach. First, designing the algorithm framework is not a trivial task. A second challenge is how do you generate good designs from the framework, even once you have it. You have to search. The more complex the framework is, the larger is the design space, the harder it is to search the design space. And then finally, once you have the design, when the system has produced a design for your data or your application scenario, how do you trust this design? How do you know it is going to work, or how to just explain how it works? So first, about designing the algorithm framework, I would say that this is one of the most challenging tasks if you are starting from zero, because you want to attain at least 3 goals. One goal is that you want to maximize the possible number of valid algorithm designs. First, you don't want to generate invalid designs because that's completely useless. But you want to maximize the number of possible valid algorithm designs because you want your framework to be flexible and to be able to apply to different application scenarios. On the other hand, you want to avoid redundancy. You don't want to have the same component under 2 different names, or you don't want to have that combinations of components lead to the same exact process than a different combination. So you have 2 different designs that are basically doing the same. And the third goal is that you don't want your framework to be too complex. You want components to have a clear role in the system and not have components that fit awkwardly between 2 roles. And towards that goal, it would be nice to define invariants and interfaces to separate roles. So once you have a component, you can clearly identify where it fits. And if somebody else proposes a new component, it's clear where this component will go in the framework and what will be an alternative to. In that sense, it's good to avoid metaphorical language. For example, when we talk about evolutionary algorithms, we might talk about mutation, recombination, but those concepts are hiding what the actual components are doing. And it would be better to define what the component is doing rather than relying on these metaphors. And this is my final point, that we should not completely trust how the components are described by the original authors, but we should look at what the components are actually doing and try to recast them or reconceptualize them for our framework to fit our invariants or interfaces. Unfortunately, this reconceptualization is hard, and well, I could talk more about this. And the other downside is that implementing all this, of course, takes a lot of time. It's much easier to say, oh, I'm going to propose a new algorithm that is changing 2 little things from a previous one, and I will publish just that. The second challenge is that once you have this framework and you can generate hundreds of thousands of designs, then you have to find a good design from this framework for your problem instances or your application scenario. And what this means is that you will have to set correctly the value of many, many parameters, the parameters that describe the components, how to generate designs from your framework. And this is not an easy problem. This is a problem called automatic algorithm configuration or hyperparameter optimization, where you have a large number, sometimes hundreds, could it be thousands, of numerical and categorical parameters. This parameter space is hierarchical. That means that for some parameters are only active or only have an effect if other parameters take certain values. And it's also constrained. There are constraints between the parameters that constrain their values. It's also a black box problem because you don't have a mathematical model of this algorithmic framework. If you want to know how a certain algorithm design performs, you have to instantiate it from the framework and run it on particular problem instances or particular data sets. And normally these problems, or the algorithms, are stochastic. So it's not sufficient to run them once. You may need to run them several times. You may need to run them on different problem instances, on different data sets. The selection of the data sets and the problem instances itself might be just a sample, a random sample, a stochastic sample from a larger set, which adds more problematic to the search. Surprisingly enough, it turns out to be that this part of the system is the one that is farther developed. We have already many tools available that are easy to use and getting better that can do this. I have mentioned already Iris, but there is also SMAC. Maybe you have heard of Optuna or Hyperband. I'm sure that there are many more that I don't have time to mention here, but there are a lot. So this problem is not really that much of a problem anymore. Of course, not everything is solved. There are still many open questions. For example, if you have an application scenario where evaluating one design takes days or weeks, then searching just becomes very, very expensive. How to incorporate multiple design objectives in the design process is also something that hasn't been studied a lot. And something that I'm personally very much interested is how a human can guide the design process. And I have done some initial work on this, but I think there is a lot to be done there. And another open question is that if the algorithms that you are automatically designing are interactive, they are meant to interact with humans, then you cannot put the human in the automatic design process. So you will need to simulate humans during the automatic design process. So how can we realistically simulate humans? In the case, for example, of automatically designing interactive multi-objective evolutionary algorithms, we have proposed to the concept of a machine decision maker. Well, a particular type of artificial decision maker, and this works here. And finally, the last the last challenge I want to talk about is understanding. So imagine you have your automatic design system. The automatic design process has returned an algorithm design for your particular application scenario. Why should you trust this design? Why the system has generated this design? What are the parameters that are important in this design? What parameters can you change and the results would be the same? Also, what happens if the data in the real world changes or the problems evolve? How robust this design will be to such changes? So these are questions that are about the explainability of the or the interpretability of the designs generated by the system. And there are some techniques available. There are some techniques that are taken from interpretable ML, from explainable AI that can be applied to this field. But I think there is still much more that can be done to add to the explainability. Personally, I think that the goal should be to end up with a kind of automatic report, if possible, with natural language explanations that is similar to the automated statistician of Garamani that, well, if you know his work, well, you will know what I'm talking about. Okay, I think I went a little bit over time, but I hope there is some time for questions. Thank you very much.
Thanks, Manuel. That was great. It's making my brain hurt because it's so meta, this whole area.
Yes, it's a bit meta, yes.
I don't know the correct level of abstraction. So we got some questions already in the chat. So I think you know Julia well. Maybe it's best if, Julia, you just say your question.
Okay, yeah, no problem. So Manuel, thanks for that talk, really interesting. I was just wondering, so the fact that you've got dependencies between different components obviously makes the statistical analysis of your results difficult because you need to reflect that. But is there, and obviously you're dealing with that challenge, but is there a danger there that, because we're essentially, so if we're telling humans to focus just on the design of individual components, we're essentially telling them to ignore that dependency in their own design step? And is there danger there that we lose out on something?
Yes, it could be through this, but I'm not actually advocating exactly that, because what where is it? Yeah, so because for me, point 3 is one of the major selling points. When many times when people publish an algorithm, I mean, I'm doing this, so I'm still using the classical approach many times because I don't have this system available for everything. When I do the classical approach, sometimes you try things and they don't work, and you never mention them in the paper. You never mention what you tried. You never mention all the things that you did there that didn't work, interactions, things that seem like a good idea and then they didn't work. Maybe you analyze some parameters, maybe you mention a few things, but there is no space to mention everything. But if you do the automatic system, then not only do you generate much more data because the system can do many more experiments than you, but also you have all this data to analyze. And is this data the one that you should use to drive your design of novel algorithmic components, not in isolation, but taking into account what has been done before? And then, yes, you can also, I mean, the system is not only to, the only thing that you do with it is not only search. You can also use the system to generate a specific designs that you want to compare and test your component with those specific designs. But I will say that still, even after you do that, you should let an automatic tool to search for new designs that maybe you never thought that could combine better with your novel component. Does this answer the question, or did I misunderstand something?
No, I think mostly, but I'll take you up on that another time. I think for some other people questions.
Okay, there's one from Varun here. Maybe I'll ask this one. So it's about how do you distinguish between optimizing hyperparameters and designing a new algorithm. So why are those kind of different levels of abstraction that are considered different things?
Yeah, so the boundary is quite blurry. I mean, normally hyperparameter optimization doesn't make a distinction between them because they are parameters. For me, the distinction is in what is the thing that you're optimizing. If you're optimizing an algorithm that is not very flexible but has a lot of numerical parameters, but the structure of the algorithm itself is kind of fixed, then I will not say that you are generating a new design. But if you have designed a framework on purpose to be able to generate new designs in such a way that when you generate a design, most of the framework is not being used. Most of the code that is there is actually not used at all, because they are alternative possibilities for what you for the algorithm that you instantiated. Then I will say that then you are generating new designs. At least that's how I see it.
Can I have a counter question on this?
Mm-hmm.
So for example, if you consider an algorithm where you have different types of mutation operator, and if you are changing the mutation or crossover operators, do you consider it's a new algorithm design or a hyperparameter optimization?
I personally will not consider it a new algorithm design. I think it's a bit too small change. Now, if you have types of mutation by types of mutation, you I don't know, instead of being a classical mutation that is 1-to-1, is some kind 1-to-many or many-to-1, and then it's not really a mutation, it's some kind of variation operator. And then the line is very blurry. Personally, I think it will be. I also will think it about. My point of view will be, or my litmus test will be, if I did this manually, if I created this design manually and I try to sell it to a journal like a new algorithm, will they consider it a new algorithm? I think it's quite difficult to say that you have designed a new algorithm if the only thing that you have changed is the mutation operator.
Thank you very much.
Does this make sense?
Yeah, thank you very much. Yeah.
Okay. I think if you go to a predatory enough journal, you can publish it. But,
yes.
So Ali has his hand up. So go ahead and ask.
Yeah, thank you, Manuel, for your talk. Hopefully this will be very quick. I was wondering what's the overlap between literature in this area and reinforcement learning, because I see a lot of similarities. In other words, can we use reinforcement learning in, for example, hyperparameter estimation in this area, or what's the connection basically?
So I think there is some overlap. I didn't discuss about many things. For example, what I describe here is mostly called offline design. You can also do dynamic design, and then the way the system behaves is more similar to reinforcement learning. There are some things from reinforcement learning that some of the methods for doing the search in the design space use. So I think there is a lot of overlap there. I could not tell you exactly right now what are the papers or the authors to look at, but I think there is a lot, probably much more. There is much more than I know about. I have focused here on classical machine learning, robotics, and optimization because they are the three examples that I know the most. But I'm sure reinforcement learning must have examples of this. For example, one thing I realized soon is that the system that Garamani proposed for the automatic statistician is actually an automatic design system in the sense that it's taking models from a design space and using an optimizer to search the design space. I will not be surprised if this approach is being used in reinforcement learning, this whole concept. My point will be that why are we doing this apart, separated from each other? When at the end we are facing similar issues, we are ending up using similar approaches. So we have to develop algorithms to search in this design space. We have to develop techniques to explain the results of these approaches. So there should be more of a convergence of methods and techniques rather than keeping this separate, because there are commonalities even though the targets of our different fields are different.
Okay, I think we've run out of time. There was a question from Marcel, which I'll forward on to Manuel. Manuel can maybe answer by email or maybe in the chat. Maybe in the chat now.
Okay.
And our next speaker, and thanks again, Manuel. That's a really interesting talk and got lots of good questions there.
Thank you very much.
So, and our next speaker is Neil Walton, and Neil is going to talk about learning and information in stochastic networks and queues. So over to you, Neil.
Okay, can everyone hear me okay?
Yeah, that's perfect.
Perfect, okay, good. Hi, I'm Neil Walton. I'm in the maths department in the university. So this is part of a tutorial paper on learning and information in stochastic networks and queues. This is with a cohort of mine, Kwang Zhu at Stanford. So the aim of this is just to give a summary of the role of learning and information in queuing systems. It's a little bit aimed at a kind of queuing theory audience, so I'll try to kind of step back a little bit as much as possible at different points in time. And the point is to talk a little bit about bridges between, say, learning theory and queuing theory. There's some sort of new results, but the intention here is just to kind of make a few connections between different areas, to do some reviewing, but not be completely exhaustive of the whole area, because there's lots of different connections one could make. Okay. And this is what I'll say, this is originally an hour-long talk, so I'm going to skip a few slides as we go along as well, just to make sure on top of things. So queuing systems arrive in lots of applications, telecommunications being a big one, the internet, telephony, also manufacturing and supply chain being particularly important recently with these kind of ride-sharing services and delivery type things. Also healthcare. Actually, I happen to be right now in the Manchester hospital trying to look at our NHS backlog, and also transport systems, an area I've also been very interested in, where there's, where queuing comes up as an application area as well. Okay. So that's sort of applications, but sort of mostly going to be talking a little bit more on the kind of theory side of things. So there are areas in sort of operations research, such as revenue management, where they're quite well-established connections between sort of information learning and decision making. Here you think of like someone typing in a search on Amazon, and that's the information that they give you. They kind of summarize this as a context, and then there are parameters associated with those, and then they can make decisions about what products to sell to people and maybe at what price as well. An aspect of those kinds of systems is they kind of tend to refresh themselves every time. So every kind of new person who comes along tends to be kind of a new entrant into the system, and so kind of you can have this kind of independence between different searches, which is not true for queuing systems. The systems don't tend to refresh themselves instantaneously after each decision, but there's an inventory that stays there that you have to keep track of over time. So that's one of the key differences and why there isn't that kind of well-established theory there perhaps as much. Okay, so organize things into 4 parts. A first part, which is on sort of approachability and a queuing policy called the max weight policy. A second part, which is about online learning in queuing systems. A third part, where we talk about kind of the use of information in decision making. And a fourth part, we're going to discuss about reinforcement learning in queuing. Okay, so the first part kind of makes connections with, say, adversarial learning. The second part, we're going to make connections more with sort of queuing and supervised learning. In the fourth part, we're going to talk a little bit about reinforcement learning. Okay. Okay, so we'll go to part 1, approachability and max weight. So there's a kind of quite a famous result called the Blackwell approachability theorem, which is sort of a generalization of 2-person zero-sum games, and the result there called the minimax theorem. Okay, Blackwell's result sort of a generalization of where you're trying to approach some convex set. Okay, and a nice consequence of Blackwell's approachability theorem is the kind of existence of these what are called regret minimizing online learning algorithms. Okay, and so you can use Blackwell's result to prove results about online learning systems. And in fact, there's a paper that goes in the other direction that says if you've got an online learning algorithm that's got good performance, meaning low regret, then you also have Blackwell approachability. Okay, and the authors of that paper, so one of them was mentioned in Manuel's talk, so the hyperband was made by Jacob Abernathy, and then there's Peter Bartlett and Elad Hazan, and they went on to kind of use that theory to develop what's called sort of adapted regularization, so ADAGRAD, and then that's now part of, say, the ADAM optimizer. So there's this kind of well-established connection between this approachability result and online learning results, which come to kind of modern gradient optimizers. The point I want to make a connection with this, there's also a connection between this Blackwell approachability result and some kind of well-known algorithms that Turing people like as well. So I'm going to talk a little bit about those Turing models as well. Okay. Okay, so what does Blackwell's approachability theorem do? I won't go into too much detail, but essentially it's a result where I can make some random walk that's controlled in time, and I'm able to make it go towards some convex set. Okay, if I'm able to get that, I say that my random walk is approachable, that I can control its behavior towards some convex set, and otherwise I say it isn't approachable. Okay. And what Blackwell proved is there's a condition for approachability, that basically if I take my state here and I project it onto the convex set, if I can guarantee that the average reward or movement I get is on basically this side of this hyperplane after the projection, then I can always guarantee approachability to the set. Okay, so it gives a condition where I can, provided the movements have this property that they lie on this side, then I can guarantee approachability or getting close to this set over here. Okay. Why is this useful in online learning? So in online learning, we kind of have the setting where they make a sequence of decisions at each time point. Okay, and let D be the sort of distributions of the decisions at decision 1, 2 up to decision P. Okay, and we'll let Ri of T be the reward from the ith decision. Okay, and the reward that I get from decision D at time T is just the average of the rewards at that time. Okay, now we can imagine that we make decisions at each time, we sum up the rewards that we receive over say some time interval with capital T. Okay, so the aim of a good learning algorithm is to make a sequence of decisions that obviously maximize the sum of rewards. Sometimes that's too ambitious a target, so an alternative is to try and optimize the regret, which says how well did the sum of rewards from my algorithm behave in comparison to the best choice in hindsight. So in this example, you can see that the rewards of this final decision seem to be a little bit higher than all of the other rewards received so far. But you don't know that in advance, and so you can say, well, in hindsight, that was the best decision, and then you can say, well, how close was my algorithm to making those decisions? Okay. So there exist algorithms which actually do quite well that are actually little o of t. So they're sort of within the same order as the best choice in hindsight. So an online algorithm can make a sequence of choices which make as good a decision as the best fixed choice in hindsight. Okay, so that's the result that essentially Blackwell proved in 1956, that's the case. In order to get that, you can essentially phrase the problem as one of these approachability questions, and you're saying that my vector of the regret, I want my regret to be as small as possible, and so we want it to be in this kind of no regret region, this polytope over here. Okay, and what you can say is for whatever decision I make, whatever state we're in, there's a decision that I can make that always belongs to that set, and so whenever I project down onto my hyperplane, there's also a decision that I can make that lies on this side. Okay, right. And so that's the result. It's originally called the Hanan-Gadam theorem, and 1956 was proven by Blackwell. Okay. Now I'm going to kind of switch gears and start to talk a little bit about queuing. So that makes a connection between this approachability and online learning algorithms, which is a well-established one that's existed for quite, for a long time, 1956. This is the kind of model that I work on quite a bit, which is called a switched queuing network. And it's sort of quite a general model of a queuing system. Here we have some arrivals that are occurring, arrival processes that are occurring over time that are adding jobs to different queues. Okay, and the queue lengths are given here. And then there are servers that can serve from the different queues and constraints on those servers over which they can serve simultaneously, okay? So in particular, in this example, there's a line between two servers if they can't serve at the same time. So in particular, I couldn't serve a job from this queue and this queue simultaneously because there's a line between them. However, I could serve a job between this queue and this queue, okay? All right, and so we set that as amongst our set of schedules and then decide to serve the jobs, okay? You can notice that the schedule I've put here highlighted in green isn't a particularly good one, because if I try to serve, you notice there's an empty queue. So it's a bit of a wasted capacity that's being used there, okay? Just to mention, this is quite a common model used in communication systems. So for example, you could think of like a network of wireless routers, which are using the same frequency. So if this wireless router is talking, then the one next to it can't talk necessarily because they'd be sort of interfering with one another, okay? Also, this is quite common in input queued switches, which are sort of core internet routers that companies like Huawei and Cisco make. And they also have this kind of, their silicon architecture means you have these kind of matching constraints, okay? And so kind of trying to optimize these systems and get as much out of them as possible is something that's, you know, quite an interesting research area, okay? Now, a famous policy that can be used there is one called the max weight policy, where you essentially solve a linear maximization over the queue lengths, which is just sort of maximizing a linear combination of the queues times the schedules. Okay, and what you can, one of the properties that the max weight policy has is it's sort of essentially able to stabilize the queuing system whenever it's possible to. So essentially it sort of achieves the best stability you can possibly hope to achieve. Okay, and this is a kind of famous result in sort of the mid-90s by two authors, Tacitus and Ephraimides, and they show that there's this good stability property associated with this max weight policy. Okay, and what we argue in the paper is actually the reason it's got these nice stability properties again is because it's an instance of this adversarial Blackwell approachability theorem. Again, you can take your queue size vector. Again, you want the queue sizes to be small or negative, over here, okay? And what you can argue is that what the max weight vector decision is always trying to do is try and maximize the gap over this hyperplane after we project, okay? And so by doing that maximization, it's essentially achieving something that lands in this region and then approaches towards the set of queues which are equal, which is 0, okay? So there's this sort of, just as this connection between online learning and Blackwell, there's this sort of connection between what's, you know, quite a widely studied set of queuing networks through this Blackwell result as well, okay? All right, so through that, we can kind of argue that there's nice connections between approachability, adversarial learning, and the stability of queuing systems, okay? Next, we're going to start to talk about connections with sort of supervised learning, okay? So we're going to keep that kind of online learning framework that we discussed earlier and discuss it in the context of queues, okay? All right, so let's go to this picture maybe. So we had our kind of picture of online learning algorithms as before, sort of over time you make decisions and you get rewards for those decisions, okay? So I can make this decision here or this decision, this one's the better one because it's got higher reward, and I essentially want to each time make the decision of which is going to give me the highest reward. And you don't know in advance what the sequence is, and so you've just got to kind of make a decision at the time, okay? I'm going to sort of turn this picture around and make it into a queuing system, okay? So imagine I've got a server here, and it can decide to serve the different jobs here according to different service modes. So it could be like a first service mode, a second service mode, or a third service mode. And in this case, the best service mode is this one because it's, let's say, the amount of time that it takes to serve that job is given by the height here. And so if I kept using this service mode, you'd notice it wouldn't take me a lot of time to process all the work in the queue. Whereas another service mode, it might take me a long time, okay? Okay, so the question is, how do things like regret impact things like queue length, okay? So just as regret is used as a kind of common metric in online learning, how does that actually impact things in terms of queuing systems? Okay, so that's one of the things we like to look into. So you can write down the regrets of the decisions of an algorithm, okay? And now a popular way of analyzing queues is through something called the Lindley recursion, which is just a way of relating the workload at time t to the workload at the previous time step, okay, sort of minus the arrivals plus the service time. That's sort of roughly what's happening there. As a sort of Turing note, we can note the director of the Turing's PhD supervisor is David Lindley as well. So David Lindley, quite a well-known British statistician. Okay, and what you can prove is that through analyzing that Lindley recursion, so you can get essentially a performance bound that compares the performance of your algorithm to the performance of the best possible algorithm in hindsight, if you see what I mean. And it's bounded in terms of the performance of the regret of the two algorithms, okay? What that means is if you've got good regret behavior, then you should have good queue length behavior. If you've got bad regret behavior, then you're going to have bad queue behavior. So essentially the quality of the algorithm has a direct impact on the queue length, which is what you'd probably expect, okay? I'll give like one specific example in a second of that, okay? So here we consider a queue with contextual jobs. So I imagine that we're kind of calling up a call center, and you go to the call center and it asks you for some information, and you put in the information, ask for your name and things like this, okay, in different parameters. And that's the context of your call, okay? And then you can imagine there's a response of how you go about serving that call based on the context information that they're giving you. So the response then, here I give as a +1 or a -1, okay, meaning -1 is a -1 customer, I service them in a -1 way, +1 is +1 customer, I want to serve them in a +1 customer way, okay? And here, a policy is going to be essentially a linear map from a set of weights on the context to either a plus or a -1, okay? And we can assume that if I guess correctly, say my +1 equals the plus of the response, then that customer gets served quickly. I've essentially routed the call in the correct way. And if I get it wrong, then they get slow service because I routed the call incorrectly, essentially, okay? So essentially we can imagine a queue like this, and this fits into the framework I've just described earlier. And there's quite a well-known algorithm for dealing with those kind of plus-minus kinds of problems. There's a famous algorithm called the perceptron algorithm, which goes way back to the 50s. And one of the nice thing about it is it can be analyzed sort of with the tools of online convex optimization. And a famous result about it, the perceptron algorithm, is it makes a constant number of mistakes, provided there's a way of separating clearly the pluses from the minuses, essentially. Okay. All right. So we can use this perceptron's mistake bound and plug it back in that theorem that we wrote down earlier. In particular, what we can say is that if you use the perceptron algorithm for categorizing the different customers' contexts as they come in, then the number of mistakes the algorithm is going to make is constant, okay? Which then means that the performance of the queue length is within a constant of the optimal behavior, okay? And indeed, after some fixed period of time, you're actually going to achieve the optimal performance thereafter, okay? So it just gives sort of an indication of how sort of things that are used, for instance, in supervised learning or otherwise, could be used in the context of queuing system, and how those results could be passed over to bounds in the performance of those queuing systems, okay? So far we've seen a way of kind of fitting adversarial learning theory within the kind of theory of queuing systems. We've also seen a little bit of how we can get kind of some supervised learning results to fit within a performance analysis of queuing systems. Remaining questions for the last couple of minutes. What questions should we learn, and what information, what impact does that information have on performance? Okay, I'll go through this a little bit quickly, but this is sort of more due to my co-author, but is interested in information and queues. What information should you store? What's the correct characterization of a system? We tend to take the view that this is taken from a paper it's sort of basically Benjamin Van Rooij and co-authors, is kind of a reinforcement learning guy and colleague of Kwang's, and he's very interested in ways of sort of characterizing, thinking of the state of a model into two categories of information: epistemic information, which is essentially model uncertainty, okay, about the parameters of the model, and aelioric information, which is uncertainty about the state of the system itself, okay. What it tends to be, we find, is that aelioric information tends to have a bigger impact on performance. So you've got to try and get the right state representation of your system if you want to try and optimize a queuing system, rather than trying to essentially fit model parameters, okay? One example that Quang worked on was one related to admissions control. So where you've got to decide if you're going to think of this like a triage at a hospital or something like this. So you're going to decide if you're going to admit someone or divert them, essentially. And there, if you can get essentially a window of information of the customers that are going to arrive, then that has a much bigger impact on the performance of the system than if you try to estimate, say, the arrival rates and the service rates of the queuing system. Okay. But it is something that happens in other systems. Here's a model, this is sort of data science. So this is, like things like a lot of data servers tend to work in this way that, when you try and make a request to a data center, you have arriving jobs that come in and there's a dispatcher which needs to make quick decisions about which servers are essentially going to serve that request. Okay, and there's this a whole area of how you go about balancing queues over different servers. In order to get those requests having a good quick response time. And again, you get the same sort of behavior where there's essentially kind of these sharp thresholds where if you save enough information, okay, or you message jobs quickly enough, there's a kind of sharp threshold where you can essentially have a good performing kind of data center to a bad performing data center, okay? But this goes further, it's true also in early telephony routing. And it's also something that's true in switch networks. If you apply something that works on the current state information in terms of queue lengths, that's much better than estimating the average arrival rates and average service rates and trying to optimize those. Okay. Okay, so that's a bit of a discussion on information. And then the final bit, sort of reinforcement learning in queues. So last summer, Mengdi Wang, who's at DeepMind, and Nicholas Gastenay, who's at INRIA, organized a workshop on reinforcement learning queuing systems as part of the Sigmetrics conference, okay? And so there's a bit of an overview of some of the things that came out of that, okay? So what's reinforcement learning? It's essentially you have an algorithm, and the algorithm basically receives from some environment a state information, reward information, and then based on that, it makes a decision with the policy that gives an action to that, and that influences the behavior of the system, okay? When the distribution of the dynamics of the system are known and the rewards are known, then this is called a Markov decision process. But if these distributions are not known, then they need to be estimated in some way, either explicitly or implicitly. And that area is the area of sort of reinforcement learning. Okay, so it's a sort of example of an algorithm there. This is sometimes called sort of linear queue learning. Okay. And, one of the things to sort of argue is actually that, the theory of reinforcement learning, though it's sort of grown, quite a bit over the last 5-10 years, is something that's been quite intrinsically linked with the development of queuing systems. So, one of the earliest examples of applying a neural network to a reinforcement learning problem was for a queuing system for essentially elevators and lifts. So there's Kreites and Bartow paper in 1996. Then the first book in the area, John Sitcliffe is a very well-known queuing theorist, as well as working in optimization and control. Also for problems like job shop scheduling, there were early reinforcement learning approaches applied there. Then Singh and Burt-Seekers for dynamic channel allocation for kind of telephony problems, and then a little bit relating to Manuel's talk, so to have things like the cross-entropy method, which is one of the first sort of policy search algorithms being used for inventory control back in 2003. Okay. But there are lots of challenges. I think the theories don't match up well. The assumptions that you make if you want to prove a result about reinforcement learning tend to assume things like bounded state space, things mix quickly, there's good stability back guarantees, tends to work in a centralized way, doesn't work in a very well in a decentralized way. In the real world, things depend on simulation. Things are continuous for a queuing system, often in the real world, and there's usually incomplete state information. So all of that, all of those facts, which, tend not to be assumed when you want things to work in reinforcement and don't necessarily apply in queuing systems. So that's one of the reasons why it's sort of difficult to get things to work. That said, there's been sort of lots of nice works available in this area. I won't go through all of them given the time constraints. But it can work nicely. So I'll just show a quick video of some work we did at the Turing. So here's an example of a traffic light simulator. So this is a commercial traffic system, and we trained, use some sort of deep reinforcement learning algorithms, very fashionable these days, to essentially try and optimize the signal control system, essentially. So it basically looks at the behavior of the traffic flows. And one of the nice things about it is that, normally when we have queuing theory, you have to kind of make very idealized models. The great thing about applying a learning algorithm is it can sort of pick up things about the kind of the way the cars speed up and slow down and get all these implicit features out, which were hard to model as a theory person. And so you can kind of fit those parts of the system in some sense, and then sort of loop in the kind of more model-based control things to try and get things to work out. So, so that was a fun project. I enjoyed working on that. Yeah, so that's and just to show this, this is the queue length behavior for different loadings of our algorithm, and this is one called Mover, which is a traffic signal control system that's used in many junctions in the UK, essentially. So that's sort of one of the main systems that's developed by the Transport Research Laboratory. So we're kind of quite competitive with that system. Okay, anyway. So, the point there is that theory doesn't stop you implementing stuff. It's good to get your hands dirty as well, like being here in the hospital looking at the data and, working with the simulators. So I enjoy the theory stuff, but I also enjoy the other side of things. And there's lots of people working in that. So in terms of hospitals, emergency response is a very common one in the Netherlands. Road traffic, like I mentioned, manufacturing and data centers. And we're starting to see more simulators coming through, which potentially allow people to actually kind of apply some of those algorithms. So there's, I think there's a lot of room there, and it'd be kind of fun area going forwards. Okay, that's enough. I'll stop there because I probably don't want to kind of take up the clock too much. So thanks.
Thanks, Neil. As a real whirlwind through
yeah, I know.
all sorts of stuff. And I didn't think I was going to hear about the perceptron learning algorithm. That takes me back.
Oh yeah, I bet. Yeah, old school, isn't it? Yeah.
So, and also nice link to Manuel's talk, because the links to reinforcement learning and some of those things like job shop scheduling, sort of classical optimization problems.
Yeah, definitely. Yeah.
So, very interesting. Any questions from anyone? Just you can just unmute if you have a question. I'll maybe ask one. Manuel's got a question. Here we go.
I have a question, because you mentioned this is something that, because I'm also starting to work on some things related to reinforcement learning, and you mentioned all the challenges that the more theoretical words of reinforcement learning have when facing queuing problems. You mentioned unbounded state space, unbounded rewards. Do you think that the solutions that are being provided when applying reinforcement learning to queuing theory can be extended to other applications where you also have the same challenges? For example, unbounded state space.
Yeah, I mean, there's one paper I listed here that looks into that. This one at the top. Yep. Infinite state space Lyapunov function provides stability, blah, blah. So that's kind of a reinforcement learning approach where you've got infinite state space. And the idea is, like, if you've got a Lyapunov function, meaning some function that, as long as you follow it, it provides stability, well, then implicitly you could learn that sort of narrows you into a certain region of the state space. And then once you're there, you kind of apply the learning algorithm there, and it sort of essentially reduces it to a finite state space problem in some sense by having this nice function giving you stability. So that's a kind of relatively recent paper looking into that. There are some slightly idealized assumptions about what the Lyapunov functions are doing there. So I think, okay. but there are some kind of slightly more plug and play kind of results starting to come through, I think. Yeah.
Okay, thank you. I will write it down.
The fact that the sort of the machine learning is coming into parts where the model isn't quite fitting the data reminds me a bit of the way that modern machine learning is replacing a lot of bits of probabilistic modeling as well, where the probabilistic model also has very oversimplistic assumptions, and then machine learning comes in with great flexibility. In the queuing case, does the machine learning kind of plug in to the queuing theory nicely, like maybe in reinforcement learning it does, or does it break the whole thing and you just have to use, you know, the machine learning approach?
I think, okay, so there's some things where people just do reinforcement learning approach or sort of like pure machine learning approach. Okay, so like you take the example of ride sharing, like the pricing algorithms tend to be using some sort of queuing model with pricing associated with it, and it's kind of model based, but actually the kind of allocations of the drivers to the things tend to be like more of like a deep reinforcement learning approach, which no one quite knows if it works or not, or, you know, so it tends to be kind of mixtures of the two. In terms of like applying machine learning in the real world to queuing, I think the great thing that it has, because queuing is very idealized often, the theory is very, you know, quite rigid in a way, you know, and the thing is, you've got great robustness results for when things fly off to infinity and get very big, but you tend not to take care of the kind of minutiae of when the queue sizes are small, which actually might be what you care about 95% of the time. And getting that sort of, I think that's sort of the space where machine learning is going to be used more, and probably, you know, is used in other areas, if you see what I mean. So,
and then your traffic one, were you learning from a emulation model? Were you learning from a model of traffic or from actual traffic? Sorry, I think
from a model of traffic, from simulations of traffic, and that's still, right. Yeah, that's still the case. I think there's still going to be this kind of like things get trained on simulations and then put in the real world, and then needs to be recalibrated essentially. So that's going to be a problem, kind of, you know, in terms of I mean, I don't think that's a queuing problem. I think that's just a reinforcement learning problem in general. That things get trained via simulation because you need enough data, and then in the real world it might not quite work. And so,
yeah. But that's quite a growing area of sort of matching real data to emulation data as well. So
yeah.
Okay, I think we've gone over time. Sorry, Neil, but
yeah, thanks for having me. Sorry. Yeah.
If anyone wants to contact Neil and ask questions, he's got a great kind of overview of a huge number of things, and actually using it for hospital queuing as well. Excellent.
We're just looking at the data at the moment.
In real time.
Yeah.
So thanks to Neil and Manuel, two great talks, actually surprisingly closely related in the end somehow, but that's through our design of the series. And see you at the next one. So thanks for coming, everyone. Bye-bye.
Thank you. Bye-bye.